Homework for chapter 9 to your left, please. One of the problems with the exercise that we finished with on Friday is the fact that when given summary data, Excel won't do this automatically. So we did a whole bunch of calculations by hand. We did the pooled variance, we did the T looking up on the critical value, we did the calculation of T by hand, and I decided this sucked. So what I did is I took both the information from our online example where I used the Z table and the information from chapter 10, question 1, and put it in an Excel sheet. And all three parts of chapter 10, question 1, the one we did on Friday, is this central column here, and it assumes that the variances are equal. It says so right there, which means I can use the pooled variance. This third column, which is a spelling error now that I notice it, that says unknown. I missed the K. I apologize. This third column assumes that they're not the same. It uses that Welch's correction formula, which you'll notice in this case results in a slightly different T calculated value, but still less than 0.025 for the p-value. And the lookup commands in Excel are based on whether we're doing a left test, a to test, or a right test. Now, we were assuming, we were checking to see whether or not these were equal means. If my null hypothesis is mu1 equals mu2, then that's a two-tailed test. But if it tells me, in the example, in the text, for example, to use a right-tailed test, then I'm going to use what they tell me to do. This is on sample problems on our Canvas page. You should download it and look at it. But the problem is that the reason I'm using this is because in here, I was given summary data. Page 374, that's the problem we were working on. Let's take a look. Problem 9 here. For a marketing class project, Bob is investigating whether seniors eat less frequently in fast food chains than freshmen. He asked 11 freshmen, 11 seniors to keep track of how many times they ate in a fast food restaurant during October. Assuming equal variances, can you conclude the mean is smaller for seniors at 5% significance? And this time, we have the actual data rather than summary data. So let's pull up this, which again is in that sample problems section on Canvas, already done for us. But this is the data file. If you want to get that data file, you can play along at home. Here we go. I'm going to download that file, and I see that information. Senior data, freshman data. So I should figure out what's going on here. And my first reaction is that I need to do all those calculations. But then I remember Excel has a data analysis package. And way over here, under data, is a data analysis option. Way on the right says data analysis. If I click on that, they give me all sorts of options. This is where we found our descriptive statistics. But I don't want descriptive statistics. That would be the summary data that we were working with last time. I would rather have this try and do all of it. And so I start looking. And in this, I see, way down at the bottom, t-tests. And there are 3 different ones, 2 of which are applicable in this case. 2 sample assuming equal variances, 2 sample assuming unequal variances. There's also at the very bottom the z-test. But I know I can't be sure about normal because I have small sample sizes. I didn't have anything about normal assumptions here, so I'm going to assume I should be using a t-test. It said in the problem, assuming equal variances, so that's the one I'm going to use. I'm just going to click OK here. And what does it ask me for? Well, where's your first variable? Where's your second variable? Well, my first variable is over there under the column saying seniors. My second under the column saying freshmen. So I click on the highlight cells, highlight the seniors for variable 1, click on the cells, highlight freshmen for 2. Do we think these are different by how much? What's the question asked? Page 375, question 9. What's it actually asked? Which means we think it might be the same. We want to know if it's different. So my hypothesized difference should be 0. Now I am going to tell it to put all the information in a new sheet. That's why new worksheet apply is checked at the bottom. But you could have it put it on this sheet if you wanted to put it somewhere right here. You could have it put it in a separate workbook. What was our significance level in this problem? And 0.05 is what's labeled as alpha. Alpha is my significance. This is set up to go. I'm just going to hit OK. And I get a brand new page, which is really hard to read, so let's make it bigger. The hell does this say? Oh, wait a minute. We were doing assumed equal variances, so we were allowed to use a pooled variance. Notice in row 7, pooled variance. It did that calculation for me. Hypothesized difference was 0. How many data values do we have? $11 seniors, 11 freshmen is 22, so degrees of freedom, 11 plus 11 minus 1 from each. Degrees of freedom is 20, DF, row 9. What does it do? It does 2 different pieces of information. Row 10 says T-stat. That's the calculated statistic. I was calling it T-calc. Cell calls it T-stat. That's what it figured out. And then we make this column a little bigger. That number right there, that's the number we would have gotten by doing mean from the first one minus the mean from the second one over the standard error. But then it gives me both options for a one-tail or a two-tail. It shows in rows 11 and 12 what happens if we do a one-tail test. It shows in row 13 and 14 what happens if we do a two-tail test. And notice the only difference between the p-value in row 11, the p-value in row 13 is multiplied by 2. Now, we were asked what question in this problem? Is the mean smaller for seniors? Now that would be Mean for seniors being smaller would mean that our critical region should be on the left. We should be doing a left one-tail test. Based on that information, the highlighted pair of rows is the information I need. If we were asked, is the mean different for seniors than it is for freshmen, we would be doing a two-tail because I wouldn't care whether it was lower or higher. But it specifically gave me a direction. That's a one-tail test. So here's my question. With this piece of information in front of me, my assumed alternative hypothesis was that the seniors are lower. The null hypothesis is that everything's okay and the difference is really the same. I haven't done any calculations to check, but now I have all this information in front of me. Reject the null hypothesis or keep it? What's your answer to the question? The data's all here. Why? Yeah, one tail. Notice that our t-stat, t-calculated version, is negative 1.8. But our critical value is 1.7. It should be negative. Why is it negative 1? It doesn't matter. I know it's symmetric. Oh, that's too small. Reject. There's another way to tell. What's the other way to tell? Our alpha is 0.05. The p-value for that test is 0.04. My p-value is small. I'm in the rejection region, that shaded area, less than 0.05. And that means that the difference between seniors eating at fast food restaurants, the average senior, is lower than the average freshman. Freshmen eat out more often. Advantage, I didn't have to do 8,000 calculations by hand, right? I like the data analysis portion of Excel, but I need to know what's going on to interpret these results. Same question, same data, different question. Is the average for eating out different? That's a two-tail test, right? According to this information, I'd set up a two-tail test. What would my answer be? Correct. I would not be able to reject the null hypothesis because there the critical value for t is 2.08. 1.8 isn't big enough. Why is it different? Going to be a really boring recording because I'm not actually doing anything under my camera, but at least you'll be able to hear me talk about all this. Why is a two-tail test not rejecting when a one-tail is? Think about the picture of the curve and what's shaded. What's different when I do a two-tail test versus a one-tail? Say again? There's two shaded areas, and each one is half the size of alpha, right? So my problem is that if the area is smaller, I have to make the cutoff lines further out to make that area smaller, right? And so what happens, my critical numbers move out. We were when we look at the p-value that's calculated here, that's smaller than my significance when it's all on one side. But if it's on both sides, 2.5% over here, 2.5% over here, I have to compare twice as much, right? So I'd really be comparing it to 0.1. That's why we use 0.08 instead. My p-value is too big. There's not enough area for me to fall in the rejection line, which is why most of the time you will do two-tail tests because they're stronger. If you reject on a two-tail, you definitely reject on the one. Don't reject on the two-tail. You could still reject on a one-tail. Questions? Now, I actually also did this same test assuming that the variances were not equal because they were just two different lines in the data analysis section. But notice what's different in my calculated statistics here. When I assume unequal variances, my degrees of freedom change. That's that big ugly correction from Welch trying to change the number of degrees of freedom, and I have to round down, and this time I end up with DF being 19 instead of 20. Now, I don't have the formula to do Welch's correction memorized. I don't want to. I don't have to. But again, even assuming unequal variances, what's the result here? Reject or accept? Reject or do not reject? I still reject. We are still doing a one-tail test if we're answering the question in the book. And that means I should be using the p-value 0.04, which is smaller than 0.05. That's rejected. Now, when my data has large outliers, Large outliers make my standard deviations go up. My standard error is based on my standard deviation, right? So if I have a larger set of outliers, I'm going to have a larger standard deviation, I'm going to have a larger standard error. That could lead to more type 1 errors. If I have a lot of data, in this case I have fairly small sample sizes, large data sets allow me to make more assumptions about normal behavior. The next question is this difference not just statistically significant, is it practically significant? Based on the information you see in the top of this table of values, how often do seniors go out to eat in the month of October, on average? Well, the 14.09 says variable 2, right? Variable 2 goes with group 2. That's our freshmen. So seniors is 10.6. So 10.6 times a month during October for seniors, 14.1, I'll round to 1 decimal, please, for freshmen. Statistically significant, yes. That's what our test said. Practically significant. It said specifically going out to eat at fast food restaurants 3.5 more times a month. The average bill at a fast food restaurant, 10, 12 bucks, something like that. So we could say freshmen are spending 35 more, 36 more dollars a month. Practical significance? I don't know. What's your allowance for the month? College students, you don't have allowances like that, right? What's your food budget for the month? Does this pay off? The practical significance is situationally dependent. And I cannot, for the life of me, guarantee you that I understand how eating out 3 more times a month during October is practically significant for this group. Questions? So, under data analysis, we've got 3 different t-tests. We're looking at the moment at the bottom 2 sample with equal variances or 2 sample with unequal variances, or the rare occasion where we know the population standard deviation, in which case we can use that z-test for 2 sample means. Questions? All right. P-values is the flip side of confidence intervals. So I could ask the same question, how do I define a confidence interval for my difference in means? So I have the true difference in means, and then I have the estimator from my samples, and I say if the confidence interval for this estimator includes 0, then there should be no statistically significant difference between these means. So the real question is, how do I get the confidence interval? Go back to chapter 9, the stuff you just gave me, and to chapter 8, the stuff you got back. How did I get the confidence interval there? I took my estimator and then I added or subtracted something. What did I add or subtract? When I was doing z-scores, I could use z, but here for the most part, I'm doing t-scores, right? And then I had to adjust, there was the standard error was involved. So I'm going to stick with the t's because this book put forth the idea that there really was very few cases where I could use the z-test. That's why I had to find an example from a different book. It's in our sample problems. And the other assumption is whether or not I assume that the standard deviations are supposed to be the same. Because when I do assume they're the same, I use the pooled variance. When I assume they're not the same, I got to use that correction for the degrees of freedom. So if my variances are equal, I take the t-value with the degrees of freedom, just like we were doing in the last example. And then I take my estimator and I either add or subtract the t-value times what? Times my standard error. But the standard error is complicated in this problem. Remember? Standard error is nasty looking. Now, somebody help me understand what the just wrote down. What the hell is this? This first square root, that's the pooled standard deviation. That's SP. But the standard error requires me to divide that by the number of things we've got, and that's the second square root on the end. This is 1 over the two populations. So that's how I get the standard error part. Isn't that nasty as hell? Yes, that's disgusting. Utterly and completely, I agree. That's gross. The one where I assume unequal variances is nicer, except for the fact that I have to use that Welch calculation. keep telling you I don't have this formula memorized and I have to look it back up every damn time. That's Welch's criteria and adjustment for our standard deviation. And I keep screwing up what I write down, so there shouldn't be one line there. That should be two separate lines, and that should be a 1. But notice this part is much nicer. Problem is figuring out the right t, because I have to do that adjusted degrees of freedom garbage. Yikes. Now, I must tell you that regardless of which version I am doing, the whole goal is to look at the confidence interval and see if 0 is in there or not. If 0 is in there, then the means are effectively equal. If 0 is not in there, then there is a difference. That would mean that depending on whether it's to the positive side or the negative side. If it's over here on the positive side, it means that mean 1 is larger than mean 2. If it's over here on the negative side, it means mean 1 is smaller than mean 2. A left tail and a right tail. Ready? Me neither. Problem number 11. In trials of an internet-based method of learning statistics, post-tests were given to 2 groups, traditional instruction, just like this, and internet-based instruction. On the post-test, traditional group, 22 students, had a mean score of 8.64, standard deviation of 1.88, while in the internet-based group, 17 students, the mean was 8.82 with a standard deviation of 1.7. Okay. I need some information here. In group 1, traditional, there were 22 students. They had an average post-test score of 8.64 with a standard deviation of 1.88. In the internet-based, there were 17 students. The average was 8.82 with a standard deviation of 1.70. I want a 90% confidence interval, assuming equal variances. All right, that's the first formula. DF is easy, but the square roots were ugly, right? So, first question. 90% confidence interval, what's alpha? Say again? 0.1. Which means we're doing t of alpha over 2. So we're doing the t with the 0.05. With what degrees of freedom? N1 plus N2 minus 2. Now, back of the book, Appendix D, go to the table, or open Excel, we can use the t calculation to get t values here. Books are in front of you, it's probably easier on the table. Flip to the table, find degrees of freedom to be 37, and give me the t at 0.05. Well, now I have everything I need to do the calculations. The calculation itself is long and not particularly pleasant. The confidence interval formula is to take the difference in the means, x1 bar minus x2 bar, plus or minus the t-value times one big square root and then another big square root. N1 minus 1 times S1 squared plus N2 minus 1, S2 squared over N1 plus N2 minus 2, 1 over N1, 1 over N2. I have the formula written down from just a moment ago. I don't have to have this recited in my memory, but now I can put all the numbers in all the right places. 8.64 minus 8.82 plus or minus 1.687 square root of N1 minus 1. 22 minus 1 is 21 times 1.88 squared. 17 minus 1 is 16 times 1.70 squared over, that number's my degrees of freedom, 37. Another square root, 1 over 22 plus 1 over 17. Out come the calculators. The difference in the means is negative 0.18. I'm going to work out each square root separately, and then I'm going to do all of this multiplication together. So, the first square root, 21 times 1.88 squared plus 16 times 1.70 squared divided by 37. I got to take the square root of that number. Square root of, wrong button, square root of. I'm going to write down all the decimals until the very end. I'll round off at the end here. 1.804367075 times, now I got to do that square root. Square root of 1 over 22 plus 1 over 17. 0.322921158.9. Now I go through and I do all the multiplying. 1.687 times 1.80475 times 0.322921158.9. Negative 0.18 plus or minus 0.98296 and a bunch more stuff. I'm going to go ahead and round that to this fourth decimal place, like the back of the book has everything in fours, so 0.9830. Do the subtraction, do the addition. I need two numbers. My confidence interval, therefore, contains 0, right? If the question was, are these different? The answer, yes or no. This is a research question in education. It would probably be phrased, is there any benefit or detriment to internet-based learning of statistics as opposed to the traditional classroom environment? You all are sitting here in a stats class. Would you be better off learning online? Not according to that data. Average performance on the post tests were not statistically different enough. The confidence interval contains 0. I would have hoped that there would have been a difference. I'd like to think I make a difference standing here talking to you all, but I could be an internet recording. Would that make it any better? I don't know. According to this, at least wouldn't be any worse. Now, I did this calculation assuming equal variance. That's why I got to use the pooled variance. If I didn't make that assumption, I'd have to use the other formula, this one, and I'd get a different answer. Wouldn't be a lot different. It would just be a little different. And hopefully, it wouldn't change the outcome of our experiment. On the other hand, I could ask you to find a confidence interval for each mean. This goes back to last chapter. All right, so let me copy down the first group. How do I get the confidence interval for just that number? I take the number I got for the estimator, and I multiply by the standard error and the t-value. But now, my t-value is different. Why is my t-value different? It's just one sample, so what's my degrees of freedom here? Right, there's only one group, so DF is 21. What's t-value? Now, with a little bit of work, you can figure out what those two numbers are. I'm going to cheat and give them to you. And I say that I believe, I am 90% certain, that the true average for people doing the traditional in-person class is between 7.95 and 9.33. When I do this again for the internet group, I need a different t-value because now the population size is different. This time my degrees of freedom is 16. What's my t-value? Now again, if I do the same calculation, I get this interval. What do you notice about the two different intervals I have? There's no zero, but remember, this is the average for group 1 and the average for group 2 should be in here, right? These overlap, right? Interval 1 and interval 2 overlap. There's no real difference between the two behaviors. I'm pretty sure nobody's going to take their intro to stats class two different ways if they don't have to, right? So what benefit is there to trying to test the same group more than once? That is our discussion for Wednesday. See you all then. Have a wonderful rest of your day. We do a lot more of these calculations in Excel moving forward. It means the recording audio is going to be more important than the recording video.